So 7.3 and 7.4, I think 7.4 wasn't listed on the weekly assignments, but it's definitely one that we should look at. So we're going to. There is an assignment there. It's just like not on the regular Canvas page. So I'm not sure what's up with that. I didn't build it. So, whoops. Yeah. 7.3 is assessing quality. Basically, we're asking yourself, is this data normal? Or really, is it normally distributed? Because for normal, that's what normal means for us. If it's normally distributed, great, we can make all sorts of assumptions on it. Things are lovely. If it's not, you can't really use some of the fun tools, but that's okay. The bigger our data set is, the more likely it is to be normally distributed. But we don't always have big data sets because a big data set is really hard to get a hold of. So it takes a lot of effort. All right, a couple terms. Normal, probability, plot. And this is a graph. It'll be a like a scatter plot graph of observed data and their expected normal scores. So we're going to look at our data values. We're going to graph those on the x-axis. Data. And on the y-axis, we're going to get our z-scores. But we're going to do this whole process backwards. So just like when we read our z-score table backwards before, we're going to look up our area and then find our z-score from that. So it's the more hassle of the two ways, just because it takes a lot more searching, but it's not difficult. It's just tedious, I guess. All right. And a normal score is the expected z-value, or z-score. So basically what we would expect. Again, we're reading it backwards. And once we graph this, we want our data to be linear, ideally. So we're going to look at our correlation coefficient. We should always be positive, I think. Can't think of a case where it'd be negative in this circumstance. So we want our R as close to 1 as possible. The higher it is, the better it is. So high R. Means our data is more normal. So how do we figure this out? We're going to get our data. And we're going to sort it ascending. SCEN. That means the smallest to the largest. This is important because the position of our data value is something we look at with this, with our I value or index. So if we don't have that, we can't, if it's wrong, our data values, the thing we're going to calculate in just a sec will be wrong. So 2, this is my f of I. And we take our I minus 0.375 all over n minus 0.25. I is our index or the position of our data value. And we'll look at some examples. Where is our data value? N, as usual, is our number of data values. That's what N always is. It's either number of data values or number of data pairs, which is functionally the same thing. You'll notice for each data value, we don't use that anywhere in our F, because this is all about the position of our data values. If it's normally distributed, this is what our z-scores should look like. And actually, this is going to give us the area. So this measure area to the left of our score. So we'll pick that right off the chart like we did before. So it's our area to the left. We don't have to add, subtract, do anything else fancy with it. Once we get that value, we're done. So then 3, we actually do that. Find our z sub I. And finally, calculate we're going to use technology to calculate our R. We're not going to go through and do that whole mess of stuff. Most of our stuff should be able to get it for us. So let's look at a data set. I'm going to give it here, and then we're going to go over to the Google Sheet to do some of this. So we've already put our data in order. This is the data we observed. And we get 31.26, 31.25, oh, 35, 31.91, 32.06, 32.37, 32.52. 1, 2, 3, 4, 5, 6. Yep, 6 data values. Okay, so this is all that's going to be given to us is our observed data. So, or just our regular data values. We've already put them in order. Now we can label our index. So this is the first number, the second, third, etc. That's our I value. It means index is where its position. Okay, and we're going to calculate a couple things, and then we're going to look up some stuff, go from there. So our F sub I is what we need to calculate, and then our Z sub I, so it's Z-score. Let me get my F equation again, because I lost it already. F sub I is I minus 0.375 all over N minus 0.25. The good thing about this formula, our N is consistent throughout this whole example, so we can get our denominator and we're done with that. So I didn't think to grab my calculator today, calculator app, thank you. All right, so my N is 6. So the F equation we're gonna use, is not an F sub I, is our index minus 0.375 all over 6 minus 0.25. I could have done that in my head, but I didn't. 5.75. Okay. We're going to find the F value. So F sub 1, we're going to take our I is 1 minus 0.375 divided by our 0.575. And I get, if we go out 2 decimals, is that what I did on here? Got one. Yeah. I get 0.11. Okay. The next one, I get clear 2, whoops. 2 minus 3.75. Oof, I need more caffeine today. Divided by 5.75. Did I type that in wrong? No, I just have that fingers. Okay, so I get 0.28. And then finally, next one. 9.8. Okay. What I have on my page here is different. Let me clean this up a little. So it means those values are probably going to be wrong. So these are all areas and they're all probabilities. So they should all be less than 1, and they are for us. So that is great. That means my z-scores are going to be wrong. Oops. Sorry, let me my page up. Okay. My z-score chart. Okay, so I'm going to write them down in my little notebook and then I will write them on the screen. So our first one is 0.11, so 0.11. This I'm gonna go negative 1.23. So it looks like this one is the closest. Negative 1.23. And then 0.28 still on this side. You look good. So negative 0.58. 0.46. Ooh, you're beautiful. Negative 0.10. 6.3. Now we're in the positives. This should be symmetric. Maybe it's not today. 0.63. Read. You are slightly closer. 3.3. 0.80. Slightly closer. 0.84. And 0.98. It's going to be way down here somewhere. 98. You're slightly closer. 2.05. Okay. So read the chart backwards, find your values. You'll have to make some judgment calls on which one's slightly closer. So that's fine. All right. Values I found negative 1.23. Negative 5.8. Did I get my Z equation wrong? No, it's okay. Once I wrote it down wrong. Negative 0.1, 0.33, 0.84, and 2.05. Same as I did there. Okay. My numbers didn't match what was in my book here, so it makes me a little. All right. We need to take our observed data and our Z-scores. So I'm going to flip to my Google Sheets, maybe. Yeah. So I'm going to put those in here, 31.26. $32.37 and 32.52. And my expected Z-scores are negative 1.23, negative 0.58, negative 0.10, 0.33, 0.84, and 2.05. I'm going to check this in a minute, but for the moment. All right, so I have my Z-scores, I have my observed data. Let's see if I can make this graph happen. Insert chart. Maybe. Oh, look at that. I don't want a line chart. I want a dot chart. So our data are, they're not the worst linear wise, but they're not perfectly linear. We would at this point find our R value. I don't know if it's going to let me do that. It's not easily on here. But we get an idea. So we can see what our data looks like. They're normal-ish if we squint a little bit. Not terrible. Okay. The last part of, let me actually label this 7.4, rename 7.3 data. All right, our last piece of 7 is our normal approximation to a binomial probability distribution. That is a lot of words. So let's get those down. Approximation to binomial probability distribution. I'm actually going to have to use this equation, but I feel like I need to tell you how to find a binomial probability for this section. So this guy here is a fancy term. So if we have n x n factorial, these are sections we skipped, which makes me sad. One notation that's not familiar to us. So n factorial is we're going to multiply n times n minus 1 times n minus 2 until we get to 1. So n times n minus 1, n minus 2, dot, 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 2, 1. It looks way more complicated than it actually is. So let's just, for funsies, calculate 5 factorial. This would be 5 times 4 times 3 times 2 times 1. So 20, 60, 120. I'm sad we skipped these sections because this is one of my areas of math that I really, really, really like, which is why we're going to take a quick detour here because I want to. But it's interesting. So what the binomial probability or the binomial coefficient, and that's what this guy here is called. If you have a group of n things and you want to choose x of them, how many ways can we do that? So we have a group n objects and want a subset of x objects. So n and x are here. Let's put it like this. N is greater than or equal to x. And our n and x are always going to be whole numbers. There's ways to do it otherwise, but no, we're not doing that. So how many ways? Oops. Binomial coefficient counts. We have a bunch of things which we're going to choose a group of them. We don't care the order we choose them, we just want a group. And then we say, okay, if I want a group of this many, how many unique groups do I have? I like the unique groups. Just how many different ways can we choose our stuff? How many unique groups do we have? Something like that. So that's a binomial coefficient. I could give you the history on how we get there, but nobody cares. If you care, let me know and I'll talk to you about it. If not, that's okay. So that's the theory, that's the background that's going on here. We're gonna make it a little simpler. We just have a binomial experiment. So to be a binomial experiment, we have three criteria. We're going to run the same experiment over and over again. And our experiment could be anything. It could just be some survey data with some probabilities. But each trial, each thing we choose has to be independent. So think about flipping a coin. If you get heads or tails each time, that is independent. What happened before doesn't change what happens now. And it has to be the exact same thing we're doing n times. And we're going to want sorry, but we would want so many successes, but that's for the main equation there. We have two possible outcomes of our experiment. It's either a success or it's a failure. Now, we can take this one and make it fit this model. So say we're looking at some survey data and we really just care about one of these categories. So we'd say, okay, category A is a success. If we're in category B, C, or D, any of the others, that's a failure. So you can take something that has more than two outcomes and make it fit this if you want to. It's not changing anything. It's not messing with the data. We're just defining it a little bit differently, which is totally acceptable. Then we'll look at the example I'm going to look at does that. We also need the probability of success must always remain constant. So our probability can't change from trial to trial. And really, this comes back up to one. Our trials are independent, so our probability shouldn't change no matter how many times we do it. If you think of the coin flip, the probability we get a heads is always 1/2. So that doesn't change from trial to trial. If we had cards and we were flipping them and leaving them, our probability does change each time. So we couldn't use that example for this. There is a little caveat. If we have a big enough population and our trials technically aren't independent, if our population is big enough, the probability difference is so small that we treat them as independent. They're close enough. So let me do that. All right, so if NP times 1 minus P is greater than or equal to 10, our data is approximately symmetric and normal. Oh, and bell-shaped, sorry. Our data is approximately normal. It's good enough for our purposes. So N, number of data. Be our number of participants, whatever. So the number of things in our group. P is the probability of success. 1 minus P then is the probability of failure. So we'll get to this slide in a second. If our N is 500 and our probability of success is 0.07, is our data approximately normal? I'm going to lose it if I don't box it. Well, let's find out. 500 times 0.07. I'm going to do this in my head. 1 minus 0.07 is 0.93. And I'm not doing this part in my head because I don't want to. And I probably can't. 500 times 0.07 times 0.93. Whoops, I typoed 0.93. I get 32.55, which is definitely bigger than 10. So our data here is approximately normally distributed. Works well enough for us. So that's where in the previous section we said if our data set is big enough, it tends to be normal. We're looking at that here. So if it's a big data set, it's more likely to look like normal-ish. All right. So first thing we do for any experiment, test the 3 things. Are the trials independent or functionally independent? Are we repeating the exact same thing n times? So if you have a survey, yeah, you're repeating it n times. Are your possible outcomes success and failure? And probabilities are the same. And then is the probability of success always constant? Yeah. So check those, and then you're going to check your NP times 1 minus P. Make sure that's bigger than 10. If it hits those 4 things, great, move on. If not, you're done. You don't have to do anything else with it. Okay, so how we find our mean is we take our number of participants times our probability. So that's the number we expect in our group. Our standard deviation is NP times 1 minus P. So the number we found up there, we can actually use for our standard deviation. All right. I'm going to look at a couple slides here. Slide 99 and slide 104. And I forgot to boot these up. Do that on the fly. Oh, good. Nothing embarrassing. We are in the morning class. Doesn't really matter. Modules. Uh, 7. Whoops. Okay. Hopefully you can see that. So we're going to use our binomial probability. According to the Red Cross, 7% of people in the United States have type O negative blood. What's the probability that in a simple random sample of 500 people, we have fewer than 30 of type O? So we would verify it's a binomial experiment. Yes, it is. Our trials are independent. We have a big enough group of people. It acts independent. The probability that you have type O blood versus a stranger has type O negative blood is the same. It's not going to change. Now, if we're looking at a family, that messes things up. But if we just have a group of strangers, yeah. So we can use binomial experiment. What they want is, did I give us a formula for this? Oh, I did. Oh, we're finding z-scores. Sorry, I'm so used to doing the regular version of this. So if we think about this one, our blood type, we have three main A, B, O, A, B, like four different types of regular blood. And the probabilities for each type is different. So how we define it is O negative is our success. Anything else is a failure. So that's how we take something that's not binary and make it binary. We say, okay, these groups are successes, these groups are failures. This works. We can move forward using this example. Okay. Z-scores, right? Yes. All right. Sorry, it's been a hot minute since I've done these like this. I'm gonna get my mean, my X value, my standard deviation. Oops. So our slide says the number in our sample was 500. The probability of success is 0.07. And we're going to use a z-score. So we're going to use that formula. It's the same formula. We're just changing the letters a little bit. So we can find our mu fairly easily. 500 times 0.7. 100 times 0.07 gives me 35. My standard deviation is 500 times 0.07 times 0.93. And we already calculated the inside value of this, but that's okay. Let's go to the other version of this. And I get square root of, I'll go this way, 32.55 is approximately 5.7. It's good enough for us. Or fewer. So that's what we're looking at. So our 30 is our X value. We're going to plug in our numbers. So our Z equals 30 minus 35 all over 5.7 gives me -5 right here. I really should remember to bring my calculator. -5. Divided by 5.7. I get -0.88. And we use our Z chart. negative 0.88 would be that as the positives. 0.1894. Probability is fairly low that only 30 of them will have, or 30 or fewer will have type O negative blood. So probably going to have more than that, or, you know, closer to that. So that's how we use this. We're going to find our mean. Find our standard deviation. Use z equals our data value minus our mean, divided our standard deviation. Look up z. So once we've decided that, yes, this is a binomial experiment, we can make this work. This, if we squint, it works fine. We find our mean, we find our standard deviation, and our z-score. And I will put these values back up here, our equations, NP, square root of NP times 1 minus P. And those are all of our values. Okay, so I said slide 104, and we will flip there quick like, maybe. This one. Okay, another binomial experiment. We have 1,000 participants, and the probability of success is 0.65. And we need to find the probability that no more than 630 adults apparently favor the death penalty. Yuck. And 65% we're calling a success is favoring the death penalty. We won't argue that, we're just as it's written. So we want the probability 630 or fewer have this opinion. And so they kind of show us the math up there, but we won't cheat that. So want prob 630 or less. So again, we're just looking up exactly what the table gives us. We don't have to manipulate that at all, which is nice. All right. Find a mean. Nope, that's not right there. Oh, just come down here. Is 1,000 times 0.65. It's 650. My standard deviation I should write this out. 1,000 times 0.65 times 0.35. Square root that thing. 15.1. Use my z-score. So z equals the data value we're testing is 630 minus our mean, which is 650, all over our standard deviation, 15.1. Again, we're going to be in the negative zone, and that's okay. 630, that's negative 20. negative 20 divided by 15.1. This is going to give me negative 1.32. And that is a really weird place for my equal sign. Then we look up our values. So the same old Z-chart. If you don't have that saved or printed somewhere, I would recommend it. All right, so negative 1.32, so there's 0, 1, 2, 0.0934. So probability 0.934. So there's less than a 10% chance that that many adults or fewer feel that way. So, all right, that ends chapter 7. The next stuff we're gonna do is chapter 8, which I think we're waiting till next time. Yeah, I have notes on chapter 8.1, but not 8.2. So chapters 7 and 8 will be on the next test. I think it's 4, 5, 7, and 8, if I remember. But 8 doesn't go through a ton, like we don't do a ton of 8, so having 4 chapters in there isn't a huge to do. And we don't go through all of 5 either, so we should be okay with that. Yeah, we should be in pretty good shape then. So I'm gonna stop my video here. Stop share and end my thingy.